So I want, so yesterday I said, in principle, we'll find out if the solution to it is that Planck is basically correct, and there's just something we don't understand about building the ladder close by, or maybe in fact we reconfirm that H0 is much higher than expected from lambda CDM. And then one of the solutions is what I call this hockey stick solution, which is basically the universe does something very funny at late times. And so if you remember, I roughly had this plot of redshift versus h, and h decreases as some function of time. It would need to, so in lambda CDM, it begins to, yes? No, today, no, sorry. You can switch it off, exactly, yes. So I had this plot which, this plot was h over 1 plus z, but the lambda CDM prediction was doing something like this, but the measurement over here was, some few sigma outside what it's supposed to be. So one way of getting some behavior like that was to sort of really change the behavior of the expansion at late times. And this would mean that you have to change h more slowly. You have to accelerate faster than a cosmological constant. So if you remember, cosmological constant was the statement that the pressure is equal to minus the energy density. So W is equal to -1. So what you would need to do is to set W to be less than -1. Okay? And I will show you in a computation that's very generic in cosmology and has been used. Actually, the version of this I will use this for inflation even, but it's one of the fundamental computations I think in this business. To tell you that if you just think about this in some standard way of, look, I'll just I'll just tweak my expansion rate. I'll do something to it to make it go faster than -1. It just does not work as the physics of this is just completely incorrect. Okay, it's a completely catastrophically unstable system. So this is whenever you have this is a violation. So it's a statement about the energy momentum tensor, and this energy momentum tensor, which has this particular property, violates the null energy condition. And the point of null energy condition is a statement that when I take t mu nu and some null vector n mu, null 0, that there exists such a null vector that this can be less than 0. And if this is the case, you can show that there are observers which would see arbitrary negative energy densities. Okay, so this is the point. So there's like energy somehow is unbounded from below, and I will show you exactly how this appears in a sort of generic system. And which will lead me to say that if you want to have something like this, you cannot do it with just some standard adding some extra matter content to the universe. You really have to play around with the theory of gravity somehow. And then this will lead me to the statement that many of the ideas which produce something like that have really been constrained by looking at the propagation of gravitational waves by LIGO. So I'll tell you exactly what this sort of thing predicts and how that's been. Yeah. Yes. It's enough for. So in the thing that I will compute, it's essentially the dark energy part. So it's the moment that you have even just if you have any species, let's go like this, you have any perfect fluid which does this, you have catastrophic instability. It doesn't have to be together with something else. But there's always something underneath which has some. So if you compensate, so if you need, okay, I mean, in reality, what you need is W less than whatever, minus 0.7 or something like that, right? So in total. So therefore, in any case, look, you'll see. Well, actually, no. From the computation, I'll be do a simplified version, so you won't see this exactly. In the computation, if you did it fully, you will see that it's enough for this one species to have this property itself. It's not the whole thing that essentially kills the. Yeah. So, okay. So let me pick a. So in order to discuss this, I need to pick some sort of model. So I will discuss a kind of very general class of things, which are known either by the name of K-essence or P of X theories, depending how you. So let me start with an action. So we'll discuss theories right now, where you have gravity, right? You have normal stuff in the universe, and you add to it an extra degree of freedom. An action which looks like function P of, in principle, some arbitrary action P of x and phi. And x here is the canonical kinetic term for a scalar field, and phi is the scalar field itself, the scalar field value. So if you want your canonical normal scalar field theory, it has P equal to x minus v of phi. This is like your normal, you know, if you want this your normal quintessence, or this is your this is quintessential quintessence, or this is standard inflation, right? So standard slow roll inflation has some potential with some power of phi in it, and a kinetic term. Okay. And this is the generalization of that, and the point of this is that the energy momentum tensor for this. You can see, let me start. You can actually just write down as being some energy density plus G mu nu so the energy momentum tensor you can show looks like this, provided that u mu you take as being the derivative of the scalar, so this requires you, since this is a velocity, this means the derivative has to be time-like. So for cosmology, this is perfect because you have a rolling scalar field, right? This thing always just in homogeneous cosmology adopts this background which is time-like. So and it's normalized by essentially the size of this the norm of this gradient. So if you pick this u, the energy momentum tensor has this form. This is an exact covariant expression, right? In any space-time, it will look like that, with the rho equal to 2x px minus p, and p equal to p of x. Right? So it's essentially, it's a very general fluid, right? So the reason I'm picking this particular theory is a very general fluid. Is it really any hydrodynamic of a perfect fluid can be represented by this? Not quite, in that what I've done is, of course, my velocity is derivative of a scalar, so it cannot carry vorticity. So I'm missing from this picture the vortical part of velocity flows. But I'll be looking essentially at small fluctuations, and I'd be working out a quadratic action for it. So if I had another degree of freedom, like vorticity would appear as a separate thing itself. So this only represents the sound waves of a fluid. It doesn't represent rotation. But other than that, it's a very generic thing. So I'm using a particular model, if you want, in order to represent something very generic. Good. So. Okay, so the computation I want to make is to work out so I want to work out the energy of the fluctuations of the system. So there's going to be some background, and this is the cosmological background, there'll be fluctuations of the scalar field. And I want to work out really what the energy of those fluctuations is. And I want to ensure that these fluctuations have positive energy, or at least, if not positive, that they're bounded from below. Because if I have so I'll work out a Hamiltonian for them, and if this Hamiltonian is not bounded from below, then you have a situation where your theory essentially can create fluctuations for free and destabilize over some time scale. And this time scale principle is as quick as any time scale you can write down inside this theory. Okay, so what I will roughly derive is let me see, how do I want to tell you about this? Okay, so what I want to do is the following. I will basically write down, I will expand this action to second order in some fluctuation. This fluctuation, think about it as being delta phi or something. So when you're working out equations of motion, you essentially perturb to first order, and then this gives you the equations of motion for the background, right? So I'm going to work this out to some second order in this expansion. This is going to be some action for my background, which I don't care about because that's just my action for the background. This is going to be the equation of motion for the background, so that's actually going to be 0 on shell. And what I will care about is this piece, which is the first correction to this background. So I'm going to get some action like that. And because I know what the symmetry of the background is, right? It's just background cosmology, FRW. So Lorentz symmetry is, so if I'm in Minkowski space, right? I have the full Poincare group. So in Minkowski, I have the full Poincare group, Lorentz transformations, etc., etc. In cosmology, I no longer have this because there is a clear definition of what is time, right? There's a spatial slice of the universe, it's homogeneous, and I know exactly what that is. And there is a particular thing that I call my time direction. If I begin to move with respect to this spatial slice, I know I'm moving because, for example, my cosmic microwave background will be boosted, right? So there's no longer a boost symmetry. What remains is really so this whole symmetry thing is broken into reparameterizations of time. So I can redefine time arbitrarily as a function of time. So I can define a new time coordinate as a function just of time. Define, I don't know, conformal time as a function of coordinate time, for example. And a rotation symmetry on the spatial slice, because it's homogeneous isotropic, so I can just rotate and clearly nothing can. So whatever this thing will look like, it has to obey this particular symmetry. So what this means is that, let me move over there. Oh, okay, more. So what this means is that my action, right, S2, whatever it is, it will have somehow time in it. It will have space, and then there'll be some terms which. So right now I'm writing this action for some completely arbitrary degree of freedom. I haven't really said what it is. I'm just trying to prepare you so you understand what I'm trying to get to, and what really I'm allowed to get. You will get something that looks like things that are scalars. Scalars of these rotations. So scalars under these rotations, or here. So the only kinds of terms I can write down. So let's say my coordinate is q, right? There's some coordinate q, some field. The only thing I can get here is some kinetic term with some arbitrary coefficient that is a function of time only. Okay. I can get some term which will contain the gradient of this field. So this is a scalar under the it's just diq diq, so it's a scalar under the rotations. It's just a length, right? It's just with some arbitrary coefficient that's a function of time. And I can include things that are functions of q itself, let's say. I'm doing this at second order, so the only thing I can write down is second order in q. So actually, I'm only writing down terms second order in q, right? Because I'm doing this expansion in second order. Which is essentially what a mass term would be, right? So there's some mass like that. Let set it minus over 2. So whatever I get will have to be of this form, and I will only get. Okay, let me just say there's some c, whatever this is, some c function of t. It's not quite enough. I'm gonna get 3 coefficients, which could be arbitrary functions of time, and that's the only thing my symmetry of the background allows me to write down. Is this clear why I'm getting this? No. Okay, let me try to get it. Maybe it will then. So, but I just want to say that. So you will see that I get so I will get an action that looks like this. But okay, so what? Who cares, right? So this is some Lagrangian for this action. Okay. And what I want to calculate energies is a Hamiltonian, right? So I have to do transform this into Hamiltonian, and the way you do it, right, is that you say Hamiltonian is PQ dot. So Q is just some generalized coordinate. P is I'm going to define as this generalized momentum conjugate to this coordinate. So I need to do the transformation like this, where P is defined as dl dq dot. So P itself is q dot. Okay, so momentum is just q dot. Actually, sorry, it's aq. So when I work out what the Hamiltonian is, Hamiltonian density in principle, because this integral over space over here, I end up with half p squared over a plus half b diq squared plus whatever c over 2 c over 2 q squared. Okay, and I want this to be bounded from below. Okay, so that means that so what these mean, so when they're just coordinates in phase space. So I can pick, under normal circumstances, I can pick any arbitrary q and any arbitrary p. So if I want this to be bounded from below, I must make sure that the whole thing has is, let's say, non-negative. That's the simplest. Or has some, at least at most, has some bound. And you can see that that's okay. This is positive because it's p squared. This guy's q squared is always positive. This guy's always a square also. So this is positive provided that all a, b, and c, that all of these guys are larger than 0. Okay. So I will try to obtain a version of this in cosmology. And in order to have a theory where the energy of the fluctuation is positive, so it doesn't destabilize, all these 3 guys have to be 0. Okay? And when you break any of this, so when it's not larger than 0, the kinetic energy is negative. Okay? And kinetic energy is negative, this is called a ghost. Okay? If you break B, this one over here, it means the gradient energy is negative. So you can create gradients for free. So this is called gradient instability or Laplacian instability or something like that. And this one is, it's called a tachyon. So if this term C here over here is negative, it means you have so this is dependent on energy, right? So if you have a momentum, if you do a Fourier transform of this derivative becomes K, right? Becomes the mode. So for high momenta, this thing is important. This one does not depend on momentum. This is just a mass term, and this is so. Okay, and any of these, you have to worry about. If they happen to, if you require, so these things represent times. So if these things are broken, if any of these are violated, right? So if any of these 3 are negative, then you have an instability in your problem. And sometimes the instabilities can be slower, you don't care. But sometimes they're extremely fast. But if your instability size is of the same order as H0 or something like that or higher, then you cannot discuss your background, because what will happen is that you will create this instability, will grow at the same rate as what you actually want to really compute as a background, and your background is no longer correct. Okay, so what I need to do is I need to work out this for my particular theory, but I'm guaranteed by symmetry that it will only look like this, because I can't write any other, I can't write anything with some di not sitting anywhere because it's not a scalar, etc. Yeah. Okay, I can't write down things that are functions of space over here, because that would not be isotropic anymore, right? So it's that's the reason why this is where you should expect from the beginning that this is this very particular fixed form. Okay. So this computation is the reason I want to do it is not exactly just because I want to prove to you this one thing, and it's not only for that. This computation is really fundamental in inflationary physics, for example. So if you ever try to work out things like non-Gaussianities and so on, the way this computation is done is the simplest that was found so far. It's done by Maldacena in 2003. So there's many ways of doing this if you want the quadratic action only. There's many ways of doing this. It's sort of slightly simpler, slightly more complicated. But if you want to go beyond that, you want to study the cubic action because you want to understand non-Gaussianity, for example, in the early universe. This is the way to do it because it's simplest, as far as we know. So what I want to do is essentially just find out, take this action here, plus gravity. So I've missed gravity from this. So I'm going to take the action minus g half r. I mean, I'm setting m Planck to 1. I'm going to expand this to second order. Now you know that in general relativity, there's lots of constraints, right? So the game here is that you want to be able to write down an action for the degree of freedom this thing will contain. So there'll be one scalar degree of freedom that you want here, because gravity, and there's going to be the gravitational waves here that are going to appear at the end of this. But you're going to have to solve all the constraints of the equations in order to show this. And the easiest way to do it is to introduce you need to split this up somehow into time and space, right? And you can choose a set of coordinates called the Adm coordinates, where you define the metric using a lapse n, a spatial metric hij with a shift ni. Okay, so you essentially have split up, if you want, the 0, 0, the 0i, and the ij parts into 3 different objects. But this is completely arbitrary. This is completely, so this is a choice of coordinates, but you can apply it in any space-time, right? So this has nothing to do with cosmology. This is purely it's a decomposition. So you do this, and good. So that's one thing you need to do. So this defines if you want so I've chosen a particular slicing of my space-time to do this, right? I've chosen a particular thing to be a time coordinate. So there is a vector which defines how my space-time is sliced, some vector u mu here. Okay. And what this means is now I can decompose the curvature in this space-time, this r, into the curvature which is into the intrinsic curvature of the spatial slice which remains here, and the way that this thing is embedded into the full space-time, which is the extrinsic curvature. And it's just an equation in differential geometry. Equation. See, my 4-dimensional Riemann, whatever it is, gets decomposed into a 3-dimensional Riemann. So it's the curvature of the spatial slice, right? plus the way the spatial slice is embedded. And here you have, let me actually do it like this, 1 over n squared. That's okay. So E mu sigma, E nu rho, and E nu rho, E nu sigma. Okay. So this is a result. It's the Gauss-Gatzke equation. It's a result in differential geometry. Which allows you to express this 4-dimensional guy into spatial, and they think that this remains. And what you'll see is that what actually happens is that in general relativity, for example, these terms are what give you the kinetic term for the graviton, and these terms give you the gradient term for the graviton. So this is kind of beautiful. It appears beautifully here, but I haven't defined this E yet. I'm sorry. So the definition of this, so 1 over n times this E is the extrinsic curvature. Sorry, it's the extrinsic curvature, which is defined as how do I do it? Let's do it like this. I'm going to write it in this way that people hate. Alpha, beta, nu. The alpha. So there's my vector u, which is the one that defines the slicing. I'm taking a symmetric derivative of it. So this is the shear of this vector field, if you want, and I project it onto some slice, this thing is an induced metric on the slice, on the spatial slice itself. So this perp object is defined as the induced metric on this on the spatial slice. Okay, so these are some, but the beauty. So this is completely covariant what I wrote down here, but actually when you plug in this metric, it all sort of becomes much more pleasant. Let me give you that. Yellow. So you end up with the action, the action for this theory, d3x dt, the root minus g becomes, otherwise root minus, this is root minus g multiplying everything here, right? This root minus g splits up into a determinant of the h metric times this guy. So there's a root h now instead. This bit, you just have, so there's an n times h, and the n cancels here. So it's 1 over n only now. Eij minus e squared. So this is the trace of this e, and this is the, and the e is defined over there. And then there is a lapse times this curvature of the 3 dimensionals, the Ricci curvature now, so it's just the trace of the Riemann, right? Ricci curvature now of the 3-dimensional slice. But this just depends on h now, plus 2kx. Okay, let me. So this is still completely exact. There's no approximations here. So now I want to expand this to second order. And the easiest thing to do is to pick a, yes? Okay, so, oh, sorry, okay. I always call it k, but I call it p because is this function p, right? Sorry about that. So now we have a so now we put into cosmology. So there's a background, which is defined as this hij here. So the hij is going to be a squared delta ij from FRW metric, right? the lapse from FRW metric is just 1 in the background. And this Ni is equal to 0. And this phi is just some phi bar. It's purely a function of t. And now I'm going to do perturbations of this. And I will define, so I need to perturb, each of these, and also each of the, and also the scalar, right? So I'm going to have a so the perturbation, the full Hij at, I'm going to perturb that and write it down as a squared times e to the 2 zeta. So inflationary physics, you will see this as the curvature perturbation. So this is the thing that everyone computes in inflation. It's really the behavior of this field. Because it's a spatial metric for the spatial slice and some scalar potential for the curvature, times Hij hat, where this Hij hat is exactly defined as having determinant 1, and this is the gravitational wave. That's what Hij decomposes into, some spatial curvature and a gravitational wave. I need to pick a gauge for this, so it's just your transverse. And then I will also pick a gauge in which the scalar field, so this is just how I'm picking my slicing, the scalar field fluctuation itself is 0. Okay. And then you just vary this thing with respect to just vary this thing with respect to the lapse. Sorry, I need to define. I need to tell you what D is. Where's the shift from? Right, let me just do one. Sorry, I need to define E in terms of these, so I don't get it wrong. So, in this basis, Eij is, where do I have it here? It's 1 over n, 1/2 Hij dot minus di nj. So, sorry, the point being that the shift only appears inside this. So, this Hamiltonian constraint, normally in general relativity, is varying with respect to n. That gives you one constraint. That's the that's the energy constraint, if you want. There's the momentum constraint, which comes with varying with respect to the shift, nj here. And, right. And those will give you constraints, which you have to solve. Okay, let me. So, really, if you're interested in details of this, just look at. I think I've given you enough if you look at that. Sorry, let me just say one more thing, because you need to know how to vary it. So when I do the perturbation, so Hij gets perturbed in this way. Delta phi, it's a particular gauge. It's called the unitary gauge. It's my choice of slicing of the perturbations. And my n becomes the background value plus some delta n. Okay. And then you can expand things like the square root of h as a cubed e to the 3 zeta. And x is just phi bar dot squared over 2 minus phi bar dot delta n over 2. You plug this in. So you get the constraints at linear order. So actually, the great advantage of this method is that when you get the constraints at linear order, that's enough, because they always appear multiplied by the equation of motion. So you solve for the constraint for n, you solve the constraint for the shift n and j, and you end up with, let me just skip to that. An action that looks like this. And I will just write this down. J dot squared minus squared dkHij squared. So once you solved all of this, you end up with the gravitational wave, and use the standard action for gravitational waves at quadratic order, kinetic term squared and gradient term squared, with this coefficient equal to 1, which means that this moves at the speed of light. And here you have the action for the perturbations of the scalar field, which you've introduced. And here you have, so this is the curvature perturbation, essentially. So this is the result that you use to actually say everything about inflation. So if you try to quantize this particular action, this is how you get the inflationary spectrum, for example. But for my purposes, this is, I did this because I think it's an important thing to understand that how to do this in cosmology, I think, today. But for my purposes, really, what I wanted to say is that, I told you that what we really care about is exactly what these coefficients are for this particular theory. And A is just 2x divided by h squared. Oh, by the way, so in standard inflation, you have a canonical scalar field. So this 2x is really just phi dot squared divided by h squared. So this is, so those who know, then this is epsilon. So this is the slow roll parameter that appears in inflation. And this is the reason why the inflation power spectrum is then looks like 1 over epsilon times the gravitational one, is because this coefficient here is small. Okay, so in standard inflation, this is epsilon, this is 1, and therefore the ratio of the gravitational wave to the scalar power spectrum is the inverse of the ratio of these coefficients. But here it's a little bit more general. Sorry, this is P. Some result like that. And the sound speed that I wrote down here. So this is really the speed of propagation of perturbations in this thing. It's minus kx over this p over d px. Okay, so now you can see from the energy momentum tensor that I wrote down here that if I write rho plus p, I get rid of this p over here. It's just equal to 2x px. Okay, so this thing is just equal to minus rho plus p divided by 2x times d. Okay. And the point of doing this was to tell you the following, is that if you look, if I want to have w less than minus 1, that means that this coefficient here, sorry, there's no minus here. No. Sorry, this coefficient here, when I have w less than minus 1, becomes negative over here. So I can make it positive by having this negative. But if this is negative, then this quantity becomes negative. So whenever I break this w equals to minus 1, either I have an instability of the system, which is to do with the gradient. The gradient energy becomes negative, or my kinetic energy becomes negative. And this thing, the only thing I have done here is I've assumed that the thing that is driving expansion, if you want, is a perfect fluid. Okay? Perfect superfluid, if you want to get technical, but because there's no vorticity. But so this is an extremely generic result, and it just tells you that you cannot do things like this hockey stick thing. Right? You cannot just arbitrarily say, oh, let me choose w less than minus 1 and see what happens. So it turns out it's possible to do this, to have this w less than minus 1, but you really have to really change the structure of the theory of gravity. So something has to change in the constraints that I've set up here. So these constraints have to do with the theory of gravity here, not to do with the theory of matter, in order to allow you to have this w less than minus 1. Okay, so w less than minus 1 means you either have ghosts or gradient instabilities. And these are very fast instabilities. So really, these are instabilities which occur at the fastest rate, which is describable by our theory. So there's a lot of so one of the alternatives to inflation is this idea that the universe is not expanding. It wasn't that the universe was expanding all the time with some accelerated expansion at the beginning, but with W very close to -1, that's the inflationary model. But there's this alternative idea, which is a bounce. So the universe first collapses and then bounces. But if you do that, you have to violate W less than -1. So this immediately tells you there's a fundamental problem. We're just saying that, so for years people were doing these bouncing models, but not without a fundamental theory because they couldn't really do this, and they didn't know how to describe the perturbations. So anyway, just to stress this, because this is kind of, in a lot of cosmology, people just arbitrarily fit W less than -1 just because it's a parameter, but without thinking that if you do that, you really have to change. But it's in principle possible to do. So it has been done in the last 10 years. People have constructed models which can do something like this. I don't particularly want to spend time on these exact models because I just want to sort of tell you about some of the physics. But we need to start with, so I'm telling you now, so the standard thing of adding some extra degree of freedom just doesn't work. You need to do something much more fundamental. And one of the things you can try to do is to modify the theory of gravity, okay? So if you try to do that, you have to deal with, from 1971, a theorem due to Lovelock. Okay? So this paper is, if you want to look at it, it's not very helpful. It's just a bunch of indexology, but it concludes that GR is a unique theory for the metric. Okay? It's a theory that describes the dynamics of the metric, provided that there is an action to start with. So it could be some emergent thing that doesn't really have an action, but then I don't know that. It's in 3+1 dimensions. Okay? It's local, so it doesn't have non-local degrees of freedom, which depend on things which are space-like separated, and has no other degrees of freedom. So essentially what that means is that the moment that you try to modify gravity, you really have to introduce, the simplest thing you can do is to introduce another degree of freedom of some sort. Okay? You cannot just say, oh, I'm going to just have a theory for the metric, which is somehow different. So let's say GR is unique. Unique if. Okay, so let me, and there should be somewhere actually that is Lorentz invariant too, I guess, in principle. So, okay. Let me split this maybe. Okay, let me skip that for the moment. So the way that you modify gravity, therefore, is by adding some extra degree of freedom. And you do something, you make it interact with curvature in some particular way. And this is sort of not completely trivial to do. So there's a very simple theory which you can just write down and it does that. But if you would like to get something more non-trivial out, you actually have to do some work. And this is a result of the fact that you are trying to add only one degree of freedom. So there's another thing that, let me do this. So there's another thing that limits you in how you can play around with theories, right? So in principle, you say I can just write anything down. So in principle, you'd say you might hope to get something that does what you need if you modify gravity by coupling curvature to some extra degree of freedom, or adding extra degrees of freedom inside gravity by adding a mass, for example. Yes? Yeah. Yeah, it doesn't really do anything here. This is really just. Okay, so here we get into philosophy. No, so here no. So I would say that what I want to do is to somehow modify this bit. Okay, and then I've added a perfect fluid here. I haven't done anything. So it's like adding dust, and is that modify gravity? Yeah. But is this a long-range force? It's just so it interacts through gravity. So if I have an overdensity of this, it will create a gravitational field, and therefore it will be an extra force, right? So, but this is massless, by the way. So I've added a massless field, right? There's no mass term here. So if you want, you have to do a much better job than this, right? So if you want, in order to do something that will solve your W equals to minus 1 problem, you need a much better job than adding something like that. It has to be more complicated. Let me tell you about another thing, which is. So I'm trying to design some theory which will describe gravity in a different way, with some extra force, which I'll need to get rid of at some point. So, because I haven't seen this in the solar system, but in cosmology maybe it appears. There's something called the Esther Gatzke theorem, which this was somebody living in the middle of the 19th century. In St. Petersburg. So what he found was that if you have so coming back to Hamiltonians, if you have a situation where you have a Lagrangian which contains more than second derivatives, which contains more than, so normally Lagrangian, the way I wrote it, I erased it already, but when I wrote down my Lagrangian, it only contained Q and Q dot, and I write down this generalized coordinate. Okay. But if you try to include higher derivatives, for example, you make a Lagrangian which depends on the second derivative here, you in fact create a Hamiltonian which is unstable. Okay. Not if it's, but then you can integrate by parts. You can integrate by parts, right? Okay. I mean, so there's either degenerate, non-degenerate. Yeah. So let me. So the point is that. Exactly. So that's a good. So there's a question. There's this thing which you need to say, which is it needs to be non-degenerate. So non-degeneracy. Non-degeneracy is a statement that when I try to find the conjugate momentum to this particular coordinate, right? So I normally do dl by dq double dot. That's what I would do. It means that this depends on q double dot. It is some function of q double dot. Okay. Which means that I'm able to solve the original. So when I want to find the Hamiltonian, I want to express in terms of the momenta and the coordinates, I can solve for this q double dot because this thing is dependent on q double dot. Okay. So this is a statement of non-degeneracy. So if it's not non-degenerate, it's degenerate, and then you cannot do it, and then it turns out there's some ways of escaping what I'm telling you. But if you want to approach things basically, like as a standard theory as possible, you would want to be able to do something like this. Okay, so what you find is that, so if this is non-degenerate, you find that okay, so what is the Euler-Lagrange equation for this, for an action contains such a Lagrangian? So it contains the standard bit, which is dl by dq, as the dl by dq dot. But there's also, you need to vary respect to this guy, which already tells you that you'll need to put more initial conditions if you do this. So this sort of fundamentally changes the way that you think about how you define your Cauchy surface. There is a bit that looks like this. If it's non-degenerate, that means that if I take a derivative with respect to q double dot, I still get q double dot. So this will contain a q quadruple dot in it. Okay, so the equation of motion will in fact be some q quadruple dot is whatever, some function of q dot, q double dot, and q triple dot. Okay, and then it turns out, which has some solutions. I can invert it and say my q is some function of all these. So there are 4 initial conditions, right? Define q, I need to have 3, 4. So there are 4 canonical coordinates. So he showed this is possible for any such non-degenerate Lagrangian. He can pick a particular coordination, which is that you say q1 is q, q2 is q dot, p1 is dl dq dot minus dl dq double dot dot, and p2 is dl dq double dot. Okay, if you do this, you can just do the Legendre transform to find the Hamiltonian for this, and the Hamiltonian looks like this. H is p1 q dot, q2, sorry, plus p2, this function, some function only containing q1, q2, and p2, okay, minus the Lagrange, with the p's and q's back solved. Okay, and from this you see the following. So remember, I told you that you want your energy to be positive, right? So Hamiltonian represents the energy bounded from below. But here I can pick an arbitrary q and an arbitrary p. So I can always pick if I have positive q, I can always pick an arbitrary negative p and find that my energy is negative. Okay, so the moment you have something like this in a system, you're dead, because you have a Hamiltonian that's unbounded from below. So really, if you have higher order derivatives here, you're just hiding another degree of freedom, really, and this degree of freedom is, some sort of it's unstable in some particular way. Okay, so these are mathematical truths about Hamiltonian systems. So, when you're playing around with doing some kind of modification to gravity, you just have to bear in mind that all this is true. Okay? So, let me, rather than sort of play around with models, let me just kind of concentrate really on when I want to modify gravity. What I would like to do, what's interesting to me right at this moment in time, is to modify, where's this action gone? Here. I would like to modify this part. So take for granted from me for the moment that there are theories that have been found where you modify, you allow it to have W less than -1, that in fact do not have these instabilities, and they modify this part of the equation. Okay, so what I would like to do for the rest in the remaining half an hour is kind of tell you about how these theories get constrained by exactly constraining various modifications to this using gravitational waves. So again, I told you that FRW is a very symmetric background, so the most I could in principle do here, right, is kind of, I'm going to write down some action for this thing. and multiply it by just, again, some arbitrary functions of time, which I'm allowed to do, just like in the case of this scalar. So MH. Okay, let's call this let me do it like that for the moment, because this is a bit complicated and I might not want to go into it. So I can, in principle, find theories where gravitational action for the gravitational waves is modified by some parameters, which is like time-dependent sound speed of tensors, some time-dependent normalization. So if you think about it, this coefficient here in general relativity is called the Planck mass. It's normalization for the kinetic term of the graviton. This is how hard it is to move the graviton. So if I change the value of this thing, what I'm doing is I'm changing the Planck mass here. So there's a change in the speed of propagation. There's a change in the Planck mass in principle. That can be a function of time. And I'm allowed to add a mass to the graviton, but a massive graviton spin-2 field can only have 5 polarizations. It's a very particular mass. I can write it down here, which looks like this. It's called the Fierz-Pauli mass term. Okay, these are the only things I can do on the cosmological background. Okay, so yes, so so let me go back to this. So the thing I want to care initially about is the speed of tensors, right? So look, I have this particular decomposition of the Riemann, of the Ricci, if you want, of the Ricci scalar in the action, and this contains the 3-dimensional. So it decomposed into a 3-dimensional part, which gave me this term, and into the extrinsic curvature part, which gave me the kinetic term for the gravitons. Okay. So if I wanted to create a theory where I have the speed of tensors different from 1, what I need to do is somehow shift the coefficients of these two terms around. Okay. So that means it tells you that somehow this theory needs to involve some sort of background that is not Lorentz invariant. So Lorentz, yeah. Exactly, yeah. So I'll get to that. Yeah. I'll get to that. That's, to me, that's interesting. I don't know if it's really ever measurable. Yeah. So. Yeah, exactly. Yeah. So I will tell you about that, but I don't really know whether it's realistic. So you can do it in principle. That's the. Anyway, so I would like to somehow shift this. So okay, one thing I might want to do is this sort of, okay, I mean, how can I do it? I need to multiply I need to introduce some sort of, simplest thing I can do is introduce some sort of scalar field which will provide my slicing, and then introduce a term which kind of is different on the cosmological, so some way of getting a different space and time parts of the Ricci tensor. So simplest thing for me to do is to introduce an extra term in the action. So when you add, that looks kind of like this. Some scalar field with some derivatives. So in cosmology, this is phi dot. So there's a particular, one of the directions is picked. And therefore, R00 will get some extra, we'll get some extra component. But you have to be careful, because if you do something just like that, this thing contains itself second derivatives of the metric. So the moment that you try to write down some equation, right, you will generate. So when you try to write down the, let's say, the energy momentum tensor for this, the Einstein equations for this theory, you will generate derivatives acting on these scalars, and you get higher derivatives, right? So for a long time, people didn't know even how to seriously write this down, at least in our community. So let me do a simpler example. If I just take, so you see exactly what happens. If I just take phi times r, and I do a variation with respect to the metric, what this ends up doing is giving a term in the energy momentum tensor that looks like d mu d nu phi minus g mu nu times box phi. Okay. So whatever, there's some derivative structure on the metric over here, which will mean that I get two derivatives hitting phi in the energy momentum tensor. So this is exactly the same thing would happen here. I take a variation with respect to g mu nu. I get two more derivatives on this, and therefore I get 1, 2, 3 third derivatives in my equation of motion. And I was telling you, if you add higher derivatives, everything is dead, and you should never look at it. So it turns out there's a sort of funny property where you can actually add a particular term, which is just in terms of second derivatives of the scalar field, which looks something like this: d phi squared, moving box phi squared, d mu nu. Wait, this times that, right? Okay, and any theory where I just write down some function g, no matter what, of second derivatives here, any theory which has this particular structure, so it contains a term like this, which is the one you want to modify the speed of tensors, and also contains a term exactly like this. It has to be precisely this term of this particular relationship here. In fact, allows you not to have any higher derivatives in the equation of motion. Okay, so this is a valid theory which contains just a scalar and gravity. So it's a valid scalar tensor theory. So these theories were discovered, in fact, a long time ago. Just no one knew about it, by a student of Lovelock called Gatzke. I think there's a paper from 1972. And he quit physics and is an artist in Waterloo. Okay. So, and theories of this type, they in fact, so you don't need to only worry about these theories being consistent in a classical sense. I'm not going to get into it, but there needs to be some, they need to be consistent as a quantum theory, at least to the extent that relativity is. And these theories have large ranges of scales on which they are valid as a quantum theory. So this is the kind of interesting fact about them, and so why people have thought about them as alternatives semi-seriously. And they have this property, they can violate the null energy condition. Okay? I have 20 more minutes now. Okay. I got 12:30, right? Yeah, okay. Okay. So it's this type of thing, right? That you need to do something like this. And so remember, let me stress, you need to have a cosmological background for this to be non-zero. Because in Minkowski space, there's no scalar field. This doesn't have a gradient, right? So this term does not contribute. On the cosmological background, where you have a particular time direction, you have a term like this. And on that background, gravitational waves have a speed that's different from 1. So it's really you might worry that having speeds different than 1 is somehow inconsistent with Lorentz invariance and so on, and it is. And the reason for it is that the cosmological background is a solution which spontaneously violates Lorentz invariance. So you're allowed to do things like this, at least as a whether it's consistent on the level of a quantum theory is a separate issue, but classically you're allowed to do it like this. Okay, anyway, so let me go back to, where was I? So yeah, now I have this equation for the action for the graviton. So let me write down the equation of motion for it. I just take a variation of that, and I get the linearized equation of motion for the call it here. So it's A dot over A, just to. So this contains. It's not exactly like it is in Minkowski. There's an extra term, which comes from the fact that there's this an overall. Oh, sorry, I apologize. There's a square root of h over here, and therefore there's an a cubed that was here that I lost. So from this a cubed, you get a correction to do with the friction of the expanding universe. So the amplitude of this thing will go down in an expanding universe. You know that because there's luminosity distance that we've discussed already. So there's a friction term of some sort here. There's this gradient term which describes the sound speed of the wave, and in principle some mass term. Okay. So I can redefine this. Hij. So I can solve this equation by defining v, which is equal to square root of a times little a, the scale factor of the universe, times h ij. So I don't care about the indices ij, right? So I should call this vij, but just bear with me. So if you do that, this equation just reduces, and you change t. This equation changes to v prime prime plus speed of tensors k squared v. Okay, I've taken a Fourier transform also to get rid of this. Plus some mu squared times v, where mu is a mass, but it's not this mass exactly, because now there's been this redefinition of the variable. Mass changes slightly, and this mass squared looks like this thing that was here already, but plus something that is a function of, let me not write the full thing. Yeah, it's a function of h squared, h dot, and a dot over ah. So a prime, this is okay. So there's some mass which is of order h, and of order this friction term. So again, if you're doing something like inflation, what you find is that this thing is negative. So this means that the gravitational waves during inflation are getting a negative mass. So that's a tachyonic instability, so it's bad. But actually, this is exactly what ends up generating the gravitational wave background that, in principle, we might one day see. So inflation roughly works like this, by creating this tachyonic instability, which is a time scale of the order of h, so you can live with it. But here, realistically, this is of order h, so the mass is of order of the size of the universe, unless this a, which is my Planck mass modification, is changing quickly. So realistically, those terms are sort of completely undetectable in anything that we might be able to build. So you have to detect gravitational waves the size of the universe to be sensitive to it. But nonetheless, it's important to see the gravitational waves in the expanding universe have a mass. That's one. So this equation, I can just write down a dispersion relation. So this is plugging in, okay, let me write down. So I can write v is equal to e to the, some v0, right, e to the I omega t minus I plug in some solution like that, some oscillating solution, and I can get a dispersion relation. Omega squared is ct squared, k squared, plus mu squared. Okay, so my dispersion relation, the relationship between the wavelength and the frequency of the wave is modified from the standard one. The one thing is that I see that there's a different speed of propagation, that's this one. And then I get this, in principle, there's some mass that I might be able to see. Okay. And So GW. So the prediction really of this is that if I have a pulse, so let me forget about mu for the moment, right? Setting mu to 0. I do that. I have a pulse of gravitational waves. It will arrive to me with speed ct instead of the speed of light. Okay, if I have some sort of, so I have some theory for gravity which involves some sort of term that looks like this. So, of course, as you probably know, the first the first NS-NS merger, which had the counterpart that was detected, immediately put a extremely tight constraint on this property. Delay of 2 seconds over a distance of 40 megaparsecs or so, which translates into C minus CT of the order of 10 minus 15. Okay, so there's a very high precision, waves of the sort of wavelength which we, for LIGO, which is 1,000 kilometers or so, propagate the speed of light. Okay, so this immediately tells you that such structures cannot really be present in the dynamics of cosmology. They could be present at some higher curvatures, but at least for cosmology, this sort of thing is irrelevant. Okay, so this one measurement really, there are multiple. So people have done a very thorough job of categorizing the sort of things you can write down when you say on a theory of gravity, which contains the metric plus one other field, scalar, tensor, vector, whatever, right? So these are categorized and known what is consistent, and many of them were predicting such a correction, and that's essentially been ruled out, at least in dynamics of cosmology, right? So on some level, all these, on some level, if you look at quantum field theories, any term you can write down, provided it satisfies some symmetries, exists. So this thing is somewhere. It's just the energy scale which you need to probe it is clearly beyond anything cosmology tests, so it's irrelevant for cosmology. But okay, so let's set CT to 1 for the moment. So now there's this mass. Can we say something about the mass? So what this means, if this exists, so now relation is this, mu squared. This also modifies my velocity, but the way to see it is defining the group velocity, and which is d omega by dk. And okay, so take a square root, take a derivative with respect to k, and then do a Taylor expansion, assuming that the k is larger than mu, and you end up getting a group velocity, which looks like this. So the correction from the speed of light that's dependent on this mass, okay? But this correction is dependent on the momentum of the mode. Okay, this means that different frequencies propagate at different speeds if you have a mass for a graviton. So you essentially see, so if this were the case, so if such a thing existed, your templates would not work, right? They would be somehow shifted. What's the word? Dephased, I think. Is that the term? They would be shifted. Different frequencies would. So in this case, longer wavelengths would arrive later than the faster wavelengths, right? So they would be shifted by the relative to each other, and you see a different wave arriving. So there's a constraint on this now. So for the first time, a constraint on the mass of the graviton, which tells you that mu must be less than about 10 minus 22 electron volts. Yeah? No. Okay. Okay, no, okay, but there is a theory, right? You can look at this theory. There are theories of massive gravity, right? there is no good. So I think the honest statement is that there isn't a good model for the early universe inside this theory. Yeah. No. No. But there is a theory which, in principle, works at least after inflation. So that's the problem. It's set the initial conditions, and then has some mass, and really looks. It doesn't exactly look like this because there's in fact an oscillation. There are two gravitons, and it's the thing that should oscillate into the other one. So it's not exactly the theory, but it has a dispersion relation looks like this. Okay. Yeah. That's right. Exactly. So yeah. So this is a much more general test because it's really testing how much the shape of the shape of the arriving wave train is distorted. But a theory which has where the graviton had a mass would do this. So there are such theories, and in fact they can do some acceleration of the universe, but the point is that in those theories the mass of the graviton, if you want to do acceleration with them, has to be of the order of h0. So in these units this is 10 to the minus 34 electron volts. So in principle this is still, you have it, it's impossible to probe this, right? This is a much. But I agree. No, I'm not a great fan of these theories. They're very contrived. But to be, I erased my. Should have gone to the other one. So another thing you can test is. Okay, let me do this. 5 minutes. Okay, let me do. I'll come back to the friction at the beginning of next lecture and then move on to something else. But in principle, you can change this dispersion relation by adding higher derivatives of space here. Okay, and so how would you do this? I mean, so this thing requires you to have fourth derivatives of space in this equation, but not fourth derivatives of time because that would kill your theory. So this is a theory which fundamentally violates Lorentz invariance. Okay, so you really somehow create these are completely phenomenological. Somehow, people have ideas for theories of gravity where maybe at very high energies, it's actually not really Lorentz invariant. And there are terms that appear that are of this form. So in principle, you can also, LIGO has tested for corrections like this. And there's some constraint from LIGO on the k to the 4 term, on this M4 if you want, right? There's a constraint from this, which I wrote down somewhere. When I worked it out. There we go. It's that this M4 needs to be larger. So remember, the larger it is, the more suppressed this thing is, so the more irrelevant it is, right? It's larger than about 10 to the, what do I have here? 10 minus 2 electron volts. Okay, so, because, we're dealing with very low energy gravitational waves, you're not really probing very high suppression scales here. So, maybe the natural scale for this might have been something related to the Planck mass or the scale of inflation, so clearly this is very, very low. But nonetheless, it's a test very similar to this one, right? Because you get the same thing. The way certain frequencies arrive at different times than the others. And this puts a constraint on 10 to 10 p. Yeah, that's right. Okay, so there is LIGO's carried out a bunch of these tests, which essentially have really shrunk the possible set of things you're allowed to do here, and have eliminated a very, very, very large fraction of the things people were looking at. So really, it's a sort of, it's a beautiful thing how one paper essentially blew up a very large part of the of the work people were doing in dark energy. Okay. So let me let you ask some questions.